Dear students, my today's topic is spectroscopic terms and their notations and their symbols. But we first take the coupling of angular momentum, means total angular momentum. We divided my lecture in two parts. First we teach you the coupling of angular momentum and then we teach you the spectroscopic terms and their notations. For simplicity, let us consider an atom whose total angular momentum is provided by a single electron. Means an atom in which only single electron is the main contributor of total angular momentum. In this category, there are many atoms such as the element of group 1, hydrogen, lithium, sodium. In these atoms, there is single electron outside the closed inner shell, except hydrogen, first atom in this group. In these atoms, the total angular momentum and magnetic moment of a closed shell are to be 0. If you take the example of sodium, then its electronic configuration is 2 at 1. Since atomic number of sodium is 11, therefore we know that the first orbit is filled by 2 electrons and second by 8 and third by 1 electron. These two orbits are completely filled and makes closed shell. Therefore, the angular momentum and magnetic moment of these orbitals has no any contribution in the total angular momentum of the atom. Only this single electron of outermost orbit is the main contributor of the total angular momentum. Therefore, the atoms like singly ionized helium, singly ionized beryllium, singly ionized magnesium, doubly ionized aluminum plus are also lies in this category. Means in these atoms there is only one electron outside the closed inner shell. Then if you calculate the total angular momentum of this one single electron, which is the main contributor to the total angular momentum, then you can say that this will be the total angular moment of atom. Okay, total in this atom, the outer electron's total angular momentum J vector is the vector sum of orbital angular momentum L and spin angular momentum S. Therefore, the total angular momentum J vector is equal to L vector plus S vector. Since in electronic motion in an atom, there are two types of angular momentum and two types of magnetic moments. You know, when an electron is revolving around a nucleus, then this motion is called orbital motion and the related angular momentum is called the orbital angular momentum. And the direction of orbital angular momentum or angular momentum is always perpendicular to the plane in which motion takes place. Means if the electron revolving around nucleus, then the direction of L like this. And we know that the electron also rotate about their own axis. This motion is called the spin motion of electron and related angular momentum is called the spin angular momentum, and whose direction is also perpendicular to the motion of the plane. And plane of the motion depend upon the orientation. If electron revolve in this plane, then S will be in this direction, and if the orientation is like this, then the direction of S is like this. When you want to add orbital angular momentum S for the orbital motion of electron around the nucleus and the spin angular momentum S, then you cannot add these two angular momentum algebraically. You can add these angular momentum vectorically. These are vector quantities. Spin angular momentum L and orbital angular momentum L are the vector quantities. Therefore, you can add these quantities vectorically. Vectorically means if L vector is in this side and S is also in this side, then you can add these vectors as per the vector rules and you find the total angular momentum. And if the direction of the total angular momentum L in this side and S in this side, then you cannot add only magnitude of these two vectors, means these two angular momentums. You can add these two angular momentum by following the vector rules of addition. Therefore, we can write in a simple way J vector is equal to L vector plus S vector. And if the L and S are in opposite direction, then you subtract to find the resultant. J is equal to L minus S. J is equal to L plus S. This is the total angular momentum. Except these, you can also read, and we teach you in previous videos, that the magnitude and direction of the orbital angular momentum is quantized. The magnitude of orbital angular momentum is quantized and given as L is equal to small l, L plus 1 h cross, where small is the orbital quantum number. Similarly, the Z component of the orbital angular momentum was also quantized. You had seen this in previous videos. And the spin angular momentum was also quantized, whose magnitude was SS plus 1 h cross and whose Z component was MS h cross. Okay. Then since total angular momentum is the vector sum of the L plus S orbital and spin, and since L and S have the definite values, means these are the quantized. Therefore, J should also be quantized. And similar to L and S, the J having the value J, J plus 1 and H cross, where J is the total quantum number, total angular momentum quantum number. H cross, you know, H upon 2 pi, where H is the Planck constant and J is the total angular momentum. And similarly, its Z component Jz is equal to Mj H cross, where Mj is the orientations of the total angular momentum. Okay. Like all angular momentum, J is quantized in both magnitude and direction. Capital J is equal to under root J, J plus 1, H upon 2 pi. J is equal to L plus minus S. Since spin angular momentum have only two values, plus half and minus half, therefore you can write this as L plus minus half. The component, the Z component or component in the Z direction, Jz of J in the Z direction is given by Jz is equal to Mj cross, where value of Mj is equal to minus J2 plus J with one differencing. In the case of a one electron atom, there are only two relative orientations possible. One relative orientations corresponding to J is equal to L plus S and other J is equal to L minus S. When j is equal to L plus S, since S have only two values, plus half and minus half, therefore only two orientations will be possible when you add S into the L, or plus half or minus half. Suppose L is equal to L, j is equal to L plus S. In this condition, j should be greater than L. And if j is equal to L minus S, then in this condition, j should be less than L. S having only two values, plus half or minus half. These are the graphical or pictorial representation of j is equal to L plus S and j is equal to L minus S. Here, for simplicity and for clear representation, we have choose the value of small l, means orbital angular momentum is 1 and S is always half. In plus half, 1 plus half is equal to 3 by 2, 1 minus half is equal to 1 by 2. This is the L plus S, L, S, and resultant we connect the tail of L to the head of the S vectorically. This is the J vector. Similarly, in minus we connect the L to the reverse. This is the plus and this is the minus S. Then we find J is equal to L minus S, 1 by 2. Now we take two questions to understand the coupling of angular momentum. Question: what are the possible orientations of J for the J is equal to 3 by 2 and J is equal to 1 by 2? Means question is saying that you calculate the possible orientations of J for J is equal to half and J is equal to minus half, and you can take small l, means orbital quantum number is equal to 1. We know that for any j, the mj values means orientation from minus j to plus j with difference 1. Then minus 3 by 2, when you add is plus 1, then you get minus 1 by 2. When you add minus plus 2 or minus 1 by 2 plus 1, then 1 by 2, then plus 1 plus 3 by 2. Minus j2 plus j with differencing 1 and all integers you can take, means plus j to minus j in integral steps. For j is equal to half, you can take minus half and plus half with difference 1, that is integer values you can take here. Okay. Now we take the second part of the lecture, spectroscopic terms and their symbols. The quantized energy states of an atomic electron are described in terms of the quantum numbers n, l, s and j. You know that the n is the principal quantum number, l is the orbital quantum number, s is the spin quantum number and j is the total angular momentum quantum number. Then quantum, we can take a label, we can add a label to the electron for recognition that in which energy states the particular electron belongs. The quantized energy state of an atomic electron are described in terms of quantum numbers n, l, s and j. The principal quantum number tells you that in which orbital any particular electron belongs. The electron having orbital quantum number L is equal to 0, 1, 2, 3, 4 means it gives the name of the suborbital, means S, P, D, F, G. If L is equal to 0, then this electron belongs to the S, and if L is equal to 1, then any electron belongs to P, and 2 for D, and 3 for F, and 4 for G, and so on. An electron for which n is equal to 2 and L is equal to 0, it means 2 and L is equal to 0 means S is in a 2s state. 2 means this is the principal quantum number and S is the orbital quantum number in which orbital it belongs. And similarly for which n is equal to 3 and L is equal to 1, this will be the n is equal to 3 means 3. We can add in front of the NESPDF and L is equal to 1 means P state. Then this belongs to the 3P state. Before we decide the terms for any particular atom, We want to know some definitions of basic terms. First, what do you understand by term? The spectroscopic term for the energy level of electrons of an atom are called terms. The spectroscopic term for the energy level of electrons of an atom are called term. The corresponding energies expressed in wave numbers are called term values. What do you mean by wave numbers? The waves lies in the unit length of a wave train is called the wave number. Unit length means 1 centimeter, 1 meter, 1 kilometer. How many waves lies in this distance is the wave number. Wave number is more suitable and more useful than to wavelength. Therefore, in a spectrum, we generally used 1 by lambda instead of lambda. Lambda is the length of the one wave, and 1 centimeter or 1 meter as you choose. Then 1 by lambda gives you the how many waves. Nu bar is the wave number. The term, what is term and what is term values? The spectroscopic term which belongs to any energy level is called the term, and corresponding energy is the term values. Multiplicity, what do you understand by multiplicity? This is very important term and frequently used in atomic spectra and molecular spectra. Multiplicity. Then you first understand it. What is multiplicity? Multiplicity is the number of different possible orientations of L and S, and hence the number of different possible values of J. Since J is the vector sum of the L and S, therefore the possible orientation of L and S gives the possible orientations of J. This is the multiplicity. The multiplicity is equal to 2s plus 1 when L is greater than S. This is very important. Multiplicity having two formula. 2s plus 1 when L is greater than S, and 2L plus 1 when L is less than S. This can be explained by a simple example. We choose the value of S is equal to half, small s is equal to half, and L is equal to 1. Then the multiplicity is equal to 2s plus 1 is equal to 2 into 1 by 2 plus 1 is equal to 2. It means only two orientations are possible. J having only two orientations. Total angular momentum having only two orientations. How? We know that J is equal to L vector plus S vector, means L minus S to L plus S with difference 1. L minus 1, what is 1 by 2, and L plus S 1 in plus 1 by 2, 3 by 2, and you see the difference between them is 1. If difference is to be more than 1, then we take more values between 1 by 2 and 3 by 2. Suppose one value is we find 1 by 2 and another value we find 5 by 2, then you take two more values, one more values 3 by 2 in between them, and there should be 3 values of J. But here is difference between 3 by 2 and 1 by 2 is only 1, therefore only 2 values possible of J. And you see from formula 2s plus 1 that only two orientations are possible. And if L is greater, if L is less than L is equal to 1 and S is equal to 3 by 2, then this formula 2s plus 1 does not work. In this condition, the formula 2L plus 1 works. If S is greater than L, then this formula 2s plus 1 for calculating the multiplicity does not work. In this condition, the formula 2L plus 1 works. The multiplicity is equal to 2s plus 1 when L is greater than S. Why? Since J ranges from L plus S to L minus 1, therefore this is the formula. And if L is less than S, then formula is 2L plus 1 for multiplicity. For S is equal to 0, if you take S is equal to 0, the multiplicity 2S plus 1, multiplicity formula in this condition 2S plus 1 is equal to 2 into 0 plus 1 is equal to 1. For S is equal to 0, the multiplicity is 1. A singlet state. This is called a singlet state in spectra. And J is equal to, in this condition, L. Because S is equal to 0, J is equal to L plus S, S is 0, J is equal to L. When S is equal to half, then multiplicity 2S plus 1, 2 into 1 by 2. 2S plus 1 means 2 into 1 by 2 plus 1 is equal to 2. You find 2. This condition in spectra is known as doublet state. Doublet means 2, doublet state, and J is equal to S plus minus half. S having value 1 by 2, therefore plus minus half. When S is equal to 1, the multiplicity is equal to 3. Since formula is 2S plus 1, then you put S is equal to 1. 2 into 1 plus 1 is equal to 3. This is called the triplet state. This is called the triplet state. If S is equal to L, as we already told you, then multiplicity given by 12 plus 1. Always remember both formulae, that is S is equal to L and L is equal to L greater than S and S greater than S. Multiplicity added to now you can read and you can learn how you can write the spectroscopic terms. The multiplicity always added to the left superscript of the term symbol is. Means the symbol was S and multiplicity was 2, then 2 is added to the superscript and left side. Suppose that here is the term is P and multiplicity was 2, therefore you can write as 2 and P, 2 and D, and so forth. Now the total angular momentum quantum number capital J is used as a subscript after the letter. That is, if anywhere write 2 P 3 by 2, then it means 2 is the multiplicity and 3 by 2 is the total angular momentum. Means total angular momentum write in the subscript in right side. Multiplicity 2 and total angular momentum J is equal to 3 by 2. You can understand well from this example. Question 1. Is 2 capital D 1 by 2 a possible term? Then you check this is right or this is written wrong. J is equal to L plus minus S. For D, L is equal to 2. And the value S is only plus half or minus half. You can add plus 1 by 2 or minus 1 by 2. Then you find two values, 3 by 2, 5 by 2, and with one difference. 5 by 2 minus 1, then you find 3 by 2. Therefore only two values possible, 3 by 2 and 5 by 2. J having only two values. And here given value of J is 1 by 2. Therefore this term is wrong, not possible. Okay. Write the values of quantum numbers L, S, J for each term. Three terms are given to you: 2 S1 by 2, 2 P 3 by 2, 2 D 3 by 2. And the task for you is that you write the value of orbital angular momentum, orbital quantum number, spin quantum number, and total angular momentum quantum number. From term S, you know that the value of L is 0. For P term, the value of L is 1. For D term, the value of P is 2, and so on, S, P, D, F, G. Now, for single electron, S having the value half, S having value half, and the total angular momentum 1 by 2, J, 3 by 2, J, 3 by 2, J. You can see here. One more important example, and you see this table for in more explained way. For term S, the value of L having 0, therefore J is equal to L plus minus S. Then J having only one single value 1 by 2, full notation. L is equal to 0 means S, J is written here, right subscript, left superscript is the multiplicity. Similarly for P, L having the value 1, J is equal to L plus minus S, 1 plus 1 by 2, 3 by 2, 1 minus 1 by 2, 1 by 2, and having difference 1, 3 by, there is only one difference between 3 by 2 and 1 by 2. If you subtract 3 by 2 minus 1 by 2, then you find 1. Then only two values are possible. You can write it this P, this is the multiplicity 2, 2, but the J values 3 by 2 and 1 by 2. Two terms are possible. For L is equal to 1 and S is equal to half, two terms are possible. Similarly for D, L is equal to 2 and S is equal to half. Therefore, you can find the value of J is 5 by 2 and 3 by 2, and the terms will be 2D 5 by 2, 2D 3 by 2. This is the multiplicity, or this is the total angular momentum, and this is the symbol represent the orbital SPDFG. Okay. Now one more important example here is that if you take the example of the sodium atom, then generally the ground state of sodium atom is described by the 3 2s1 by 2. It means the principal quantum number is 3. You know the atomic number of sodium is 11 and atomic configuration 2 at 1. Therefore, for one single electron in third orbit, n should be 3. This is the 3. And for ground state 2s1 by 2 means n is equal to 3, L is equal to 0 for s electron, and s spin is equal to half. Hence J is equal to L plus minus half, and you find only one value is 2. Since L is the 0, you find only one values, and you can read the multiplicity 2 is the possible orientations of total angular momentum J, but here J having only one values, and multiplicity says there should be two orientations of J. How this is possible? Then B told you that this is the convention, and for consistency B take this value is 2. All other atoms of this group, to make consistent with all other atoms of this group, we take this value is 2. Okay, therefore we can say that the spectroscopic term tell you that which electron belongs in which energy states. Okay students, thank you, and in next video we will teach you another topic like Zeeman effect or some other topic, fine structure. Okay, thank you, take care.